Hi guys, my name is IBM and I am solving October-November 2023 papers. I will be solving paper 2.2, component 2.2, that is October-November. So without wasting time, I would like to take you to the question paper. So this is the question paper. It is October-November 2023. So you can print the paper, you can find it on the websites, and then you follow through with the paper. So without wasting time, I'll just go to the questions. You can read through the instructions, you can read through the formula and the quantities given. In the following list, underline all the quantities that are SI base units. The SI base units are not expressed in terms of any other units. So these include the electric current and time. Remember, these are 7. Apart from electric current and time, you talk about mass, you talk about length, you talk about luminous intensity, you talk about amount of substance, and I think you talk about absolute temperature. So 1, 2, 3, 4, 5, 6, 7. There are 7. Current, time, mass, length, luminous intensity, amount of substance, and absolute temperature. Under certain conditions, the distance the distance s moved in a straight line by an object in time t is given by that equation. Of course, this equation has been obtained from s equals to ut plus a half at squared. That means the initial velocity must have been 0. So for this part to be 0, and for us to have a half at, for us to use this equation, acceleration must be constant, so the body must be moving in a straight line. So state two conditions under which the above expression applies to the motion of the object. Number 1, initial velocity. This is a repeated equation from last year, or from May, June, I think. Initial velocity or initial speed is 0. That's one condition. Initial speed is 0. The second one, the acceleration must be constant. Acceleration is constant. And of course, it should not be 0. If we are to use that equation, the acceleration cannot be 0. So acceleration is constant. Something is wrong with my pen. So acceleration is constant and not 0. Because if it is 0, then it is useless. So the body must, acceleration is constant and not 0, and motion is in a straight line. So the motion is in a straight line, okay. The variation with the time t of the velocity v of the car that is moving in a straight line is shown in the figure. Okay, so we have a graph of, these are straight lines, so that is constant gradients. But one gradient, this side the gradient is positive, this side the gradient is negative. So the acceleration on one side is positive, the acceleration on the other side is negative, which means there has been, that means a deceleration. Okay. Compare qualitatively the acceleration. Qualitatively, we don't need to quote values. The acceleration of the car at time t equals to 8 seconds and at time t equals to 14 seconds. Let's check. 8 seconds, of course, the acceleration is the gradient of this line. 14 seconds, the acceleration is the gradient of the other line. So first of all, in magnitude, you check the gradient. You notice that the gradient of this line would be 20 minus 0 divided by 12 minus 4. So that is 20 divided by 8. The gradient of the other line is going to be 20 minus 0 divided by 16 minus 12. That is 20 divided by 4. So you notice that the gradient of the second line is bigger than the gradient of the first line. In fact, the gradient of the second line, if you divide 20 by 4, that is 5. If you divide 20 by 8, 20 divided by 8, that is 2.5. So the gradient of the first line is a half of the gradient of the second line. Second line is twice. But second line is negative, first line is positive, so they're in opposite directions. Okay, so let's start with the magnitudes. The magnitude of acceleration at t equals to 8 is less than the magnitude of that at t equals to 4. The magnitude of acceleration at t equals to 8.0 seconds is less than that at t equals to 14.0 seconds. Then direction, of course, the direction is opposite. I would also say the magnitude of the acceleration at t equals to 8 is half that at t equals to 14. I've already verified that by calculation. The direction of the acceleration of at t equals to 8 is positive, or is opposite. I would just say is opposite. So direction of the acceleration at t equals to 8.0 seconds is opposite. Is opposite to that at t equals to 14.0 seconds. One is positive, one is negative because of the gradients are in opposite directions. Then determine the magnitude of the acceleration of the car at t equals to 4 seconds. So at t equals to 4 seconds, now some people will think it is 0 because it's along the x-axis. It is a straight line through t equals 4. It is the same for the acceleration at 4 is the same at 8, is the same at 6, the same at 10, the same at 12, because this is a straight line. So I just find the gradient taking just 2 points on that line. So the acceleration is equal to the gradient, even if I don't use 4, after all, it is a constant gradient. So that is change in v over change in time. So I'll just simply take 20 minus, I'll take the whole line. 20 minus negative 10 or 20 minus 0, whatever, the answer is the same. 20 minus negative 10 divided by the time is 0 to 12 minus 0, which is 30 divided by 12, which is 2.5. Alternatively, you can say acceleration is, I will say 20 minus 0 divided by, I think the time was 12 minus 4, which is 2.5. Or I can take 0 minus negative 10 divided by 4 minus 0. I could say acceleration is equal to 0 minus negative 10 divided by 4 minus 0, which is still 2.5. Then the car is at point x at time t equals 0. Determine the magnitude of the displacement of the car from x at time t equals to 12 seconds. The car is at point x at t equals to 0. Determine the magnitude of the displacement of the car from x at time t equals 12. So we want total displacement from 0 to 12. So displacement is a vector quantity. This part here shows distance in one direction, and this part here shows distance in another direction. So the difference is going to be the displacement, and the distance is the area under the graph. So this is a triangle where this is the base and the height is 20. 12 minus 4 is the base. Then we have another triangle here where this can be the base and this can be the height. they're in opposite direction. So I'll simply say distance is equal to the area under the graph. So the displacement is going to be, for the upper graph, is a half. The base was 12 minus 4, and of course the height was 20. That is area of a triangle. Then for the top graph, for the bottom graph, it is a half. The base was 4 minus 0, which is 4, and the height was 10. So this is distance in one direction, this is distance in the opposite direction. That's why we subtract. So from my calculator, we have 0.5 times 8 times 20, so that is 80. 80 minus 20, which is going to be 60 meters. So the answer here is going to be 60. Then a high altitude balloon is stationary in still air. A solid sphere is suspended from the balloon by a string as shown. The volume of the balloon is 7.5 meters cubed. Total weight of the balloon, string, and sphere is 65 newtons. The upthrust acting on the balloon, on the string, and the sphere is negligible. So upthrust is negligible. That means the viscous drag is the one which is going to be equal to the weight if there is equilibrium. Calculate the density of the air surrounding the balloon. So we now know that the weight is equal to mass times gravity. Mass is density times volume, then times g. So the weight is given as 65 newtons. So this is 65 newtons. So I want density. Density is going to be 65 divided by g, which is 9.81 times v, which is 7.5. So 65 divided by 9.81 times 7.5. So that is 0.883. 0.883. The string breaks, releasing the sphere. That means the initial acceleration is the acceleration due to gravity. State the magnitude of the acceleration of the sphere immediately after the string breaks. So immediately after the string breaks, of course, air resistance starts coming in. That means immediately after the spring breaks, the acceleration is very close to 9.81. So I'll just say approximately 9.8. Maybe it has started reducing, but not significant. That's why I'm saying 9.8 instead of 9.81. So immediately air resistance is approximately 0. So the acceleration will be very close to 9.81. That's why I've written 9.8. State and explain the variation, if any, in the magnitude of the acceleration of the sphere when it is moving downwards before it reaches terminal velocity. Remember, terminal velocity, here acceleration becomes 0. So it means it must have been decreasing. So resultant force, which is mass times acceleration, is the weight minus the viscous drag. Remember, the upthrust was negligible. So as it falls, viscous drag is directly proportional to speed squared. Viscous drag or air resistance increases with the speed. So as speed increases when it is falling, V increases. That means if V increases, it means the difference becomes smaller. That means the resultant force decreases, which means the acceleration also decreases. So we are saying air resistance acting on the sphere increases. Of course, it increases with the speed. That means the resultant force resultant force on the sphere decreases. And from F equals to ma, the magnitude of the acceleration decreases. As simple as that. The sphere has a mass of 4 kilograms. Calculate total resistive force acting on the sphere at the instant when its acceleration is 1.9 meters per second. So total resistive force. So I used capital V for viscous drag or resistive force. So I know that the resultant force is given by mass times acceleration. But the resultant force is equal to the weight minus the viscous drag. I'm using V for the resistive force, which is the viscous drag. So the mass times the acceleration is going to be the weight, which is mg minus the viscous drag. So when I make V the subject, it means V is going to be equal to mg minus ma. So I'll just substitute. So the viscous drag, which is the resistive force, is going to be equal to mg, which m is 4 times g, which is 9.81, minus ma, where m is 4 times the initial acceleration, which is 1.9 at that instant. So I'll just press my calculator. 4 times 9.81, then minus 4 times 1.9. So this is giving me 31.64, which is approximately 32 newtons. This V is not standing for speed, it's standing for viscous drag. So the answer is going to be 32. You can use a different letter for the total resistive force, or you can write FR for total resistive force. Question number 3, a vertical rod is fixed to the horizontal surface of the table as shown. A spring of mass 7.5 grams is able to slide along the full length of the rod. The spring is first pushed against the surface of the table so that it has an initial compression. I'll call that one X. The spring is then suddenly released so that it leaves the surface of the table with kinetic energy 0.048. So this is initial kinetic energy. Assume that the spring obeys Hooke's law and the initial elastic potential energy of the compressed spring is equal to the kinetic energy of the spring as it leaves the surface of the table. Air resistance is negligible. So they're telling us that the initial elastic potential energy initial elastic potential energy of the compressed spring is equal to the initial kinetic energy. So it means this is going to be a half mv squared is the same as a half k x squared. So I'll take this and this, and this, because they are the same. So the initial kinetic energy is 0.048, which is equal to the elastic potential energy, which is a half kx squared. So we want to find the spring constant for that compression. So x is going to be 2 times 0.048 divided by k. We want to find k. So k is equal to 2 times 0.048 divided by x squared. X, remember, was 2.1 centimeters, so that is 2.1 times 10 to the power of minus 2, and this is going to be squared. Okay, so 2 times 0.048 divided by 2.1 exponent minus 2, this is squared, so that is 217.9. 217 point, is it 0.9? No, 0.7. 217.7 is going to be our spring constant. You can write 220 newtons per meter to two significant figures. Then calculate the speed of the spring as it leaves the surface of the table. Speed, since the kinetic energy is equal to a half mv squared, so it means the speed is going to be 2 times the kinetic energy, which is 0.048, divided by the mass. The mass was given as 7.5 grams. So this is going to be 7.5 times 10 to the power of minus 3. And this is going to be under the square root. So I'll check with my calculator. 2 times 0.048 divided by 7.5 exponent minus 3. Then I find the square root of the answer. So that is 3.58. So this is 3.58. 3.58 to three significant figures. The spring raises to its maximum height up the rod from the surface of the table. This causes the gravitational potential energy of the spring to increase by. So the spring rises to its maximum height up the rod from the surface of the table. This causes the gravitational potential energy of the spring to increase by 0.039. Okay. Calculate for this movement of the spring the increase in height of the spring after leaving the surface of the table. So we know that the increase in gravitational potential energy, the increase in gravitational potential energy is equal to mgh. So the increase is 0.039. The mass is 7.5 times 10 to the power of minus 3. G is 9.81. Then times h. I'll just check my calculator. 0.039 divided by open brackets 9.81 times 7.5 exponent minus 3. So this is 0.530 to three significant figures. So h is 0.530 meters. 0.530 meters or 0.53 meters. Then calculate the average frictional force exerted by the rod on the spring as it raises. Remember, it is initially having kinetic energy. It is going to lose the kinetic energy as it gains potential energy and does work against friction. So I'll say the loss in kinetic energy should be equal to the gain in potential energy plus the work done against friction. So the loss in kinetic energy, so of course it is going to be losing the kinetic energy which we had as 0.048. So this becomes potential energy which was 0.039. And the work done against the friction is force times the distance, which is going to be times the height. Force times distance, which is going to be the height. So it means the force is going to be equal to 0.048 minus 0.039 divided by the distance, which is the height, divided by 0.530. So 0.048 minus 0.039 divided by 0.530. So that is 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. 9. 0.0169. So this is 0.016. Now write 0.017. 0.017. That is to two significant figures. 0.017. Let me check it again. 0.048 minus 0.039 divided by 0.53. 0.017. So the answer here is going to be 0.017. Okay. The rod is replaced by another rod that exerts negligible frictional force on the moving spring. The initial compression X of the spring is now varied in order to vary the maximum increase in height delta H of the spring after leaving the surface of the table. Assume that the spring obeys Hooke's law for all compressions. On the figure, sketch a graph to show the variation of X of delta H. Numerical values are not required. Okay, so since it is the kinetic energy which is going to be the elastic potential energy, the kinetic energy is the one which is being converted into the elastic potential energy, and you know elastic potential energy is a half k x squared. So I'll simply say the kinetic energy, and they are saying there is no friction. It means all this becomes gravitational potential energy. So it means the loss in kinetic energy becomes the gain in gravitational potential energy because there is no friction. So the loss in kinetic energy becomes the gain in elastic potential energy, which becomes, so the loss in elastic potential energy becomes the gain in kinetic energy, and the loss in kinetic energy becomes the gain in elastic potential energy. That means a half kx squared, which was kinetic potential, which was elastic potential but became kinetic, is going to be the gain in potential energy, which is mg times the change in height. Okay, so when you look at this, you notice that the gain in height is directly proportional to the square of x. Delta h is directly proportional to the square of x. So this means this is going to be a curve which has an increasing gradient. You can check. Why is that possible? Assuming the other factors are constant, let's say x is 0. It means the change in height is going to be 0. The graph starts from the origin. Let's say x is equal to 1. It means the change in h is going to be a constant times 1. So they are almost the same. Let's say x equals to 2. It means the change in height is going to be a constant times 4 because it is x squared. When you say x is equal to 3, it means the change in height is going to be a constant times 9 because it is 3 squared. So you notice that h increases more rapidly than x. That's why I'm saying it is a curve with an increasing gradient. So it is a smooth curve of an increasing gradient like the one I've just drawn. Okay. A ball Y moves along a horizontal frictionless surface and collides with the ball Z as illustrated in the views from above. Okay, so this is initial condition, then after the collision. I'll just go to the question. Calculate the component of the final momentum of the ball in the perpendicular direction to line PQ. So line PQ is in the horizontal. We want ball Y perpendicular to PQ, so we need the vertical component here of ball Y. We need that component, so we shall resolve the speed of 3.7 to the vertical, and that will become 3.7 sine of 27 when I resolve in the vertical. So I will say component, the component of momentum is simply going to be 0.25 times 3.7 sine of 27 degrees. So 0.25 is the mass. Remember, momentum is mass times velocity. So 0.25, that is the mass, times the velocity, which is 3.7 sine of 27, which is 0.420, 0.42. So that is 0.42 Newton seconds. By considering the component of the final momentum of each ball in the direction perpendicular to line PQ, calculate mz. So upwards is 0.42. It should be equal to downwards by conservation of momentum. So the momentum in the vertical downwards, the speed here is 5.5 sine of 44 degrees. So times the mass of z, that's the momentum downwards. So by conservation of momentum, the momentum of z, the mass z times its velocity, which is 5.5 sine of 44, should be equal to the momentum upwards, which is 0.42. Because there was initially no momentum in the vertical, total momentum in the vertical should be 0. That's why I'm equating them. It is equal but opposite, which gives us 0. So if I press my calculator, I'll just divide this by 5.5 sine of 44. And this is giving 0.1099, which is 0.11. So mz is going to be 0.11. During the collision, the average force exerted on y by z is Fy, and the average force exerted on z by y is Fz. Compare the magnitudes and directions of Fy and Fz. Remember, these forces by Newton's third law, the forces are equal but opposite. So the magnitudes, that is automatically equal by Newton's third law, and 3, that is Newton's third law, but the directions are opposite, as simple as that. Equal but opposite. Two blocks A and B move directly towards each other along a horizontal frictionless surface, as shown in the view from above. The blocks collide perfectly elastically. So that means relative speed of approach is the same as relative speed of separation, or kinetic energy before collision is the same as kinetic energy after collision. But they have not given us their masses. Before the collision, block A has a speed of 4 meters per second and B has a speed of 6 meters per second. After the collision, block B moves back, so it changes direction with a speed of 2. So I'll say velocities to the left, to the right positive, velocities to the left negative. This one moves back, so this they said B moves back, so it moves to the left, to the right. So its velocity is positive. After the collision, block B moves back along its original path. So its velocity is positive. I'm saying velocities to the right hand side are positive. Velocities to the left hand side are negative. Okay, so by using a simple fact that the relative speed of approach is equal to the relative speed of separation, speed of approach to the left, to the right, it is positive 4 minus, the word relative means you subtract the speeds, minus, but it is to the left, so it is minus negative 6, should be equal to, let's say the speed of A after the collision is V, then because B moves to the right, its velocity is speed, its velocity is positive, so it will be V plus, V minus, let me see, blocks collide perfectly elastically before the collision. Block A has that speed, and block B has a speed of 6 meters per second. After the collision, block B moves back, to the right. Okay, so I will start with B. I will start with the velocities to the right. So this will be 2 minus the velocity of the other, and let it be V. Okay, so when you simplify this, this is going to be 10 equaling 2 minus V. So this means V is going to be equal to negative 8. So it means the speed of A after collision is most likely going to be 8 meters per second, but this one will be to the left. The negative just shows that it would move to the left, because when I collect like terms here, it will be negative 8 meters per second, which means it would move to the left. The negative, I'm saying velocities to the right, positive, velocities to the left, negative. If I get a negative answer, it just means that the velocity of A will be to the left. So the answer there is 8. Then this is waves. A beam of vertically polarized light is incident normally on a polarizing filter as shown. The transmission axis of the filter is initially vertical. The filter is then rotated through an angle of 360 degrees. While the plane of the filter remains perpendicular to the beam, on the figure sketch a graph to show the variation of the intensity of the light in the transmitted beam with the angle. So we know that intensity varies, like as I equals to I naught cos squared theta. So if theta equals to 0, you just check with your calculator. Cos of 0 is 0, so this will be I naught, so that will be maximum. If theta equals to 90, cos of 90 is 0, so this goes to 0. If theta is 180, cos of 180 is negative 1, but remember it is squared, so it becomes maximum. If theta is 270, that is automatically 0. If theta is 360, it is negative 1, which is, let me check, cos of 360, it is 1, which is squared, it is 1. So we have those points. So I will now just sketch the graph. So the graph would be something like this. I think I need to sketch a better graph than this one. So the graph is a sine curve, which is of that shape. You can sketch a better one, not straight line, just curves. It is just a curve. Okay. The intensity of the light in this incident beam is 7.6 watts per meter squared. When the transmission axis of the filter is at an angle theta to the vertical, the light intensity of the transmitted beam is 4.2 watts per meter squared. Calculate the angle theta. So I have already seen that I is equal to I naught cos squared theta. This is called Mal's law. So so it means cos squared theta is equal to I divided by I naught. So I is, the transmitted is 4.2 and I naught is 7.6. So I'll just find theta. Theta is going to be equal to the cos inverse of the square root of 4.2 divided by 7.6. So 4.2 divided by 7.6. Then you find the square root of the answer. Then you find the cos inverse of the answer, which is 41.98. 41.98 degrees, or approximately you can write 42. State what is meant by diffraction. Of course, we know that diffraction is the spreading of a wave into regions of geometrical shadow as it passes through a narrow slit. As it passes through a narrow aperture, as it passes through a narrow aperture, or it passes through a narrow slit. That is what we call diffraction. Okay. Then a beam of light of wavelength 4.3 times 10 to the power of minus 7 meters is incident normally on a diffraction grating in air, as shown. Okay, so this is wavelength lambda. We have theta, diffraction, angle of diffraction, third order, where n is equal to 3. The third order diffraction maximum of the light is at an angle of 68 degrees to the direction of the incident light beam, catching the line spacing d. So we know that for a diffraction grating, n lambda is equal to d sine theta. So d is going to be n, which is 3. Wavelength is 4.3 times 10 to the power of minus 7. Divide by, I'm making it the subject, so I divide by sine of 68. So I'll just press my calculator. 3 times 4.3 exponent minus 7 divide by sine of 68. That is 1.39 times 10 to the power of minus 6 meters. Determine a different wavelength of visible light that will also produce diffraction maximum at an angle of 68 degrees. So theta is 60, and we have to check the values we're just going to check the values of n. So since we know that n lambda is equal to d sine theta, d is going to be the same, sine theta is going to be the same. So it means the wavelength is going to be d 1.39 1.39 times 10 to the power of minus 6 sine of 68 divided by n. So I will check for n equals to, of course, I will not check n equals to 0 because that will be infinite. I'll check n equals to 1. For n equals to 1, this is simply going to be that times sine of 68. This is 1.29 times 10 to the power of minus 6 meters. I think for the visible range is 7 times 10 to the power of minus 7 meters up to 4 times 10 to the power of minus 7 meters. This is red and this is violet. That is visible spectrum. So this is outside. Then I'll check for n equals to 2. For n equals to 2, it is 1.39 times 10 to the power of minus 6. For n equals to 2, wavelength is that. For n equals to 2, wavelength is that. Sine of 68 divided by 2. So I'll just divide the answer by 2. Divide that by 2, it is 6.45, or approximately 6.5. So this is approximately 6.5 times 10 to the power of minus 7 meters. And this one is in the range of visible. So the answer here is going to be 6.5 times 10 to the power of minus 7. As simple as that. Next is electricity. A metal wire has a resistance per unit length. This is R divided by L of 0.92. The wire has a uniform cross-section area, so this is area. Actually, the resistivity. So we know that resistance is equal to rho L over A. And we have R over L is equal to rho over A. So rho is going to be R over L times A because they've given us R over L. That is 0.92, then times cross-sectional area, which is 5.3 times 10 to the power of minus 7. 0.92 times 5.3 exponent minus 7. So that is 4.88 times 10 to the power of minus 7. Yes, ohm meters. A battery of EMF E and negligible internal resistance is connected in series with a fixed resistor and a light-dependent resistor as shown. The resistance of the fixed resistor is 1400 ohms. The intensity of the light illuminating the LDR causes it to have a resistance of 1600. A voltmeter connected across the LDR reads 6.4 volts. Okay, so that the current is this. So from Ohm's law, current is going to be the PD over R. So the current, we want current in the LDR, so we want the PD across the LDR, which is 6.4, over the resistance of the LDR, which is 1600. So I just check with my calculator. 6.4 divided by 1600, which is 4.0 times 10 to the power of minus 3 amperes. Then calculate the number of free electrons passing through the LDR in a time of 3.2 minutes. We know that current is equal to the charge over time. So it means total charge, which is the number of free electrons times the charge of each electron, is I times T. So the number of free electrons is going to be the current, which is 4.0 times 10 to the power of minus 3 times the time, which is 3.2 times 60, to change it to seconds, divide by E, which is 1.6 times 10 to the power of negative 19. So the answer there times 3.2 times 60, then divide by open brackets 1.6 exponent minus 19. So this gives us 4.8 times 10 to the power of 8. So times 10 to the power of 18. 4.8 times 10 to the power of 18. So that is the answer there. Then calculate the EMF E. Calculate the EMF E. So the EMF is of course going to be the PD across the LDR plus the PD across the fixed resistor, or EMF is equal to, since we know that total current, since they are in series, it means the current is equal to the EMF over total resistance. So it means the EMF E is going to be the current times total resistance. So the current is 4.0 times 10 to the power of 3 minus 3, because they're in series, the current is the same. Total resistance is the sum, which because they're in series, we have 1600 plus 1400. So this is going to be 1600 plus 1400, then times 4 exponent minus 3. So the EMF is 12 volts. Then determine the ratio. Power dissipated in the LDR divided by power dissipated in the fixed resistor. Power in the LDR over power in the fixed resistor. So we have already seen that power is equal to I squared times R, or it can be I times V, or it can be V squared over R. So I will use, let me use the simplest, which is I squared R. So the ratio is going to be I squared for the LDR. The current is the same. I'll leave the I squared. Resistance of the LDR is 1600 over I squared times the resistance of the fixed resistor is 1400. So I'll just divide 1600 by 1400, which is 1.14. Alternatively, you can use V squared. We can use V squared. Let me see. Okay, we know the PD across the LDR, this is 6.4. The PD across the fixed resistor is 12 minus 6.4, which is 12 minus 6.4, which is around 4 point or 5.6. So you can just use that. You can say 6.4 squared divided by the resistance, which is 1600. Then divide by, for the other one, the PD across it is, I hope, 12 minus 6.4. That is 5.6. So I'll say 5.6 squared divided by the resistance of the fixed resistor, which is 1400. When you divide, you'll get the same answer. Or you can use IV, whatever. Then the environmental conditions change, causing a decrease in the resistance of the LDR. In B, the temperature of the environment does not change. Temperature of the environment does not change. Of course, the resistance of the LDR does not depend on temperature of the environment. Resistance is inversely proportional to the light intensity. State whether there is a decrease, increase, or no change. The intensity. So the environmental conditions change, causing a decrease in the resistance. So if the resistance decreases, the light intensity increases. So this one increases. That is an increase. Then the current in the battery. Resistance has decreased. So since total resistance decreases and the current is equal to EMF over total resistance, since this has decreased and the EMF is constant, then the current has increased. So this one increases. Then the voltmeter reading. Since the voltmeter is connected across the voltmeter is connected across the LDR. The voltmeter is connected across the LDR where the resistance of the LDR has decreased. The resistance of the LDR is decreased. The current has increased, which increases the PD across this. So it means the PD across the LDR decreases. So I'm saying PD across 1400 increases. That means PD across LDR must decrease by conservation of energy. Both of them cannot increase, since the EMF must be the sum of these two PDs. It increases here because the current has gone up. Then it must decrease here. So this one decreases. Okay. Then last question. In the following list, underline all the particles that are not fundamental. So fundamental particles are not made up of anything. Baryons are made up of quarks, so they are not fundamental. Nucleons are protons and neutrons, which are made up of quarks. So it is the positron and the neutron, the positron and antineutrino, which are fundamental particles here. Then a nucleus of thorium decays in stages by emitting alpha particles and beta minus particles to form a nucleus of lead. So thorium, I'll write TH, which is 230 and 90, is decaying to give lead, which is Pb 20682. In stages, it is emitting alpha. Alpha is 4, 2. Let's say it emits X alpha particles plus Y beta minus is 0, negative 1. So calculate the number of alpha particles and number of beta particles. So to begin with, alpha, by conservation of nuclear number, I have 230 on the left, should be equal to 206 plus X times 4, which is 4X, plus Y times 0, which is 0. So this gives me X. X is 230, 230 minus 206 divided by 4. So X is 6. So there are 6 alpha particles. Then to find the number of beta particles, I'll consider the number of protons. So 90 equals to 82 plus X times 2, which is 2X. Then Y times negative 1, which is minus Y. So I have 90 minus 82 But remember x is 6, so we have 90 equals to 82 plus 2 times 6 minus y. So 90 is equal to 12. So 12 plus that is 94. So when minus y, when I collect it, like when I solve this, y is going to be equal to 4. So therefore, beta minus what? A meson has a charge of minus e, where e is the elementary charge. The quark composition of the meson includes a charm anti-quark, charm anti-quark. Set and explain a possible flavor type of the other quark in the meson. So we know that the charge of charm anti-quark is going to be, a charm quark has positive 2 over 3e. So if it is charm anti-quark, it is going to be negative 2 over 3e. Okay, but total charge is minus e. So let the other quark be q. Remember, meson has a quark and an anti-quark. So let the charge of the other quark be q plus negative 2 over 3e should give us negative 1e. So when I collect like terms, I have that q is equal to negative 1 over, negative 1. So that is negative 1e plus 2 over 3e. LCM here is 3. So we have 3, this is over 1. So it is minus e minus 3e plus 2e, which gives us negative 1 over 3e. So the charge of the other quark is minus 1 over 3e, and this is either down, it is strange, or it is bottom. So state and explain the possible flavor of the other quark. So it is down, or strange, or it is bottom. These are the quarks which have a charge of minus 1 over 3e. So I think that is the end. That is the end of paper 2.2. See you in paper 2.3.